Bismillahirrahmanirrahim. Assalamu alaikum. This is Faryal Javed, rule number 21TE07 from Telecommunication Engineering Department, UT Texila. So today we are going to solve lab manual 5 of digital signal processing, that is representation of discrete time digital signal into a frequency domain. Moving toward lab objective of this lab, that is basically a representation of discrete time digital signals into a frequency domain. The resolution of spectrum, computation of magnitude, phase and power spectrum, the spectrum leaking and avoiding spectrum leaking. So moving to our task one of discrete Fourier transform calculation. Basically, a discrete Fourier transform is a signal that is being converted from time domain into a frequency domain. It has various applications like in communication system, signal processing, image processing, and many more. Where understanding the frequency characteristic of signal is important for the analysis and processing. Going towards the formula of discrete Fourier transform, that is x of k summation x of n e raised to power minus j 2 pi k small n over capital N. So basically this x of k is the kth frequency component of signal in a frequency domain. The x of n is the nth sample of signal in time domain. This capital N is the number of samples in the signal. J is the imaginary unit and e is the natural logarithm. Then we'll have the formula of inverse discrete time Fourier transform, that is 1 of n summation x of k e raised power j 2 pi k small n over capital N, where this n is considered as length of signal, but it may vary by adding trailing zeros. So moving to our task one of today's lab, that is make your own functions by DFT, my IDFT, for calculating discrete Fourier transform and inverse using above given formulas. So we'll have x of 1, x of 2, x of 3 and x of 4. So the output of this lab is as follows. So here this my DFT function basically calculate the discrete time Fourier transform of given signal using formula provided in the prompt, and then the my IDFT. Yes, here my IDFT calculate the inverse discrete Fourier transform of a given set of DFT coefficient using the provided formula. Then we'll use the example that the code demonstrate the usage of my DFT and my inverse DFT function with four different input signals, that is 1, 2, 3, and 4. And then we'll compute the DFT and IDFT for each input signal and display the result, basically the DFT coefficient and the reconstructed signal for each input signal. Here the graph basically shows the original signal and their reconstructed signal in separate subplots. As you can see, the real parts of the reconstructed signal is plotted to visualize the comparison. And then moving towards lab task 2, that is frequency resolution can be enhanced by adding trailing zeros. Calculate the DFT for following signals and observe the change in the frequency spectrum. Then and here we'll have x of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, and then the number of samples are given, that is 4, 8, and 16. The output to this lab is this. So this MATLAB code basically calculates the discrete Fourier transform for a set of signal with varying length, including trailing zeros, and plot their magnitude and phase spectrum. So here the addition of trailing zeros enhance the frequency resolution, allowing for more detailed observation of frequency components in the signal. And then the rest of the code is similar to the previous one. Moving to our task 3, that is use of MATLAB built-in functions. Let we have an arbitrarily signal x equals to 1, 2, 3, 4, and then we'll use the built-in function, that is fft bracket x, and we also need to apply an inverse discrete Fourier transform to time domain representation. So the output to this task is given here. So this MATLAB code basically demonstrates the use of built-in function to analyze a signal in both time and frequency domain. And here we have calculated the magnitude spectrum and frequency spectrum too. So it basically defines an arbitrary signal x, and it calculates the discrete Fourier transform of signal x using FFT function, obtaining the frequency spectrum. So it extracts the real and imaginary part of frequency spectrum using this real and imaginary these functions, and then it compute the inverse DFT using IFFT function to obtain the time domain representation of signal. It plot the original signal in time domain and its magnitude and phase spectrum in frequency domain using stem function, and finally displays the time domain representation of signal in the command window. Overall, basically the purpose of this code is to illustrate how to analyze and visualize signals in both time and frequency domains using MATLAB built-in function for both discrete time Fourier transform and time inverse discrete Fourier transform. Moving to our last task of today, that is calculate DFT and plot magnitude spectrum, phase spectrum, and power spectrum for signals in task 2. Observe the effect of zeros padding, and the output to this code is given below. So here in this code we basically calculate the discrete Fourier transform and plot the magnitude spectrum, phase, and power spectrum for the set of signal from the task 2. And the basically the code defines several signals, the x of 1 to x of 11 from task 2, and these signals have different length and may include a zero padding. So the code calculates the DFT of each signal using the FFT function, resulting in frequency spectrum from x1 to x11. Three anonymous functions are defined to calculate the magnitude, phase, and power spectrum of given frequency domain. These functions take the DFT output as an input and return the corresponding spectra. So, this zero padding and discrete Fourier transform basically involve adding zeros to end of signal before computing DFT. This technique basically improves the frequency resolution by increasing the length of the resulting spectrum and creating additional frequency bands. The zero padding does not add any new information to the signal but can help interpolate frequency components and improve frequency estimation accuracy. So, this is it from my side. Thank you. Allah Hafiz.